All right, so optimization 4.4, Stewart calculus text. This is number 3, section 4.4. All right, so again, we're trying to optimize. So number 3 talks about this. A rectangle has a perimeter of 100 centimeters. So here's our constraints. These are the parameters that we're putting on the values in question. So the rectangle has a perimeter of 100. If you want to give that a little sketch out, you can. So we got a rectangle. Oh, it's frozen? Sorry. There we go. The rectangle has a perimeter of 100. So I'm just going to draw a rectangle. Okay. The perimeter is 100. And we're talking about, the second part says, what length and width should it have so that its area, and here's what we're trying to maximize, is a maximum. Okay. We're trying to optimize the area, make it a maximum. All right. So let's do that over here. So area comes from, when we're trying to find the area of a rectangle, comes from, I'll do L here, length, times width. Okay, so we've got length, L is length, W is width. So on a rectangle, I have, let's do length as the longest one, and width is the shortest one. So the first part, the constraint part, talks about the perimeter, and it has to equal 100. So I'm going to make an equation for the perimeter being 100. So 100 has to come from the sum of all the sides. So that's going to be 2 W's and 2 L's. Okay, so the width, the length, and the length all added together. So remember, we want to have 2 equations. One is the quantity we're trying to optimize, in this case, area. And you can have 2 variables, no problem. The second one, you want to have the constraint in an equation form. 2 variables, great. Use the same variables. Now, this next step is we have to get one equation with only one variable. So I'm going to have to substitute something in here. I want to have either, everything to do with L over here, like A in terms of just L, or A in terms of just W. And it doesn't really matter which one you pick. So over here, what you got to do on this one is solve for either W or L. So it doesn't really matter. Let's solve for W here, okay? So I'm going to do 100 minus 2L equals 2W. And then I'm going to divide all of this by 2 to get W by itself. And so I see that the width actually is described as 50 minus L. So now what I can do is I can write area as a function, okay? And we're just going to have one variable involved here now. So L is L, and the W now is 50 minus L, you see? So this is going to be L times 50 minus L, and we've successfully written the area function in terms of L only, one variable only, and it includes, in that equation, it includes my constraint, so the perimeter being 100. So this includes the constraint of the perimeter being 100, okay? Any questions so far? You guys are good? You're with me? All right, so it's good. 2 equations, one is optimization, one is a constraint. Rearrange things so you can substitute to make one equation with one variable. Now what we want to do is we understand that wherever there's an optimization, either a max, right? If there's a max for this function, area, remember this is a function of L, so if there's going to be a maximum, we are going to be looking for a critical number where the derivative equals 0, and that's where we're going to have either a max or a min. So in this case, we're looking for a critical number, so we have to find the derivative and then let that derivative equal 0. Okay. So let's do that. A prime of L is, now we can do the product rule, but remember, we don't want to do product rule if we don't have to. So a good idea is to simplify this this a little bit. So let's just do that. I'm going to make a little room here, and this A of L is actually, let's multiply this in, so we have 50L minus L squared. That's going to be much easier. It's easier for us to take the derivative of a polynomial. So if you can substitute or simplify, good idea to do that. Okay, that looks funny there. It's 50L. Okay, so now the derivative of this function with respect to L, of course, is 50 minus, now we'll use our power rule, 2 times L, and then 2 minus 1 is just 1. So 50 minus 2L. So that's our derivative. Okay with that? Good with that? Okay. So now that we have our derivative, this is the expression of the derivative, and that's the expression of all of the tangent lines, remember? So I want to find the tangent line when the x value when the tangent line equals 0, so I'm going to let this expression for the tangent line equals 0. So I want to find out where the L is that makes the slope of the tangent line to this function up here, the slope 0. So where's the L that makes the slope 0? So we'll just simply solve for L here now, just like we did in grade 5, really. Okay, take that over there, divide by 2. L is 25. Okay, L is 25. That's reasonable. It's a positive number. That's great. If you got more than one critical number and it was like plus or minus 25, remember, because it's a length, you only take the positive one. So this is a positive value. This looks pretty reasonable that this could be our length. So we will assume so. Now, if we're going to try and find the width, then we go back to this, this part here and notice that I did outline what the width was equal. It was 50 minus L, so let's do that. So width is 50 minus L is 25. So it looks like the width is 25 as well. Interesting. Okay. So a rectangle could have all equal sides, right? A square is actually a rectangle as well. So all squares are also rectangles, because rectangles, the definition of a rectangle, opposite sides are parallel, and each corner is a 90-degree angle. So that's what makes a rectangle, and squares are rectangles as well. Okay. All right. So it appears that the length and width are 25 and 25, and the area is to be a maximum. So what we can do is we can check to see if there are other values for W and L that would fit, and see if the area using other values for length and width that fit the constraints, to see if those areas are larger. So for example, if this had to add up to 100, one other possible, so this is our check, okay? And you don't have to do this, but it's a good idea to at least think through this. What could some other possible, we could have 30, the width could be 30. Let's say if the width was 30, then that's 30 and 30 is 60, and then the length here, or the top and the bottom, would be 20. Is that right? So we have 50 and 50 is 100. So we could have a rectangle like this, and let's just check and see what the area is. Let's see if it's bigger than 25 squared, because the area here is 25 squared, right? So let's see, this is 30 times 20, so this area is 30 times 20, which is 600, and 25 squared, is that 625? 625, I believe. So this area is smaller than this area. So that means we have a maximum area. We're good to go. So this is smaller. Okay? So now that we've confirmed that this length and this width are the ones we're looking for, a word problem should end with a word sentence. So we want to make sure we do that. The length is 25 centimeters, and the width is 25 centimeters. I believe we're talking about centimeters in the perimeter, right? Yeah, so the unit of length was centimeters, so that means that the length and width have to be centimeters as well. Okay, so let me know if you have any questions at all about number 3 there before we move on, because we will do number 4 as well.